So good morning and welcome to the last morning session. It's my pleasure to introduce Tomoyuki Ichiba from, sorry, I should have prepared, from University of California. And he will talk about stochastic equations with reflection. Thank you, Tomoyuki.
Thank you, Kilian. Thank you very much. My name is Tomoyuki Ichiba from Santa Barbara, California. I'd like to talk about directed chain stochastic equations, stochastic differential equations with reflection. I'm interested in dependent structure of stochastic processes in the network. So this is with reflection and the network. I like to thank all organizers as well as Newton Institute for generous support and kind invitation. I'm very happy to be here and work together, learning new stuff, good inspiration from all the talks. So let me start with without reflection, a directed chain stochastic equation. I'm interested in, as I mentioned, dependence of stochastic processes. So let me start with a pair, x and x tilde. X and x tilde here. X is described by this equation, stochastic equation. Here we have drift v naught and the diffusion coefficient v1 assumed to be smooth, depends on the time s. X itself and bracket represents the distribution of x s theta. Theta represents the initial value, dependence on the initial value, and x tilde, which is also stochastic process, next to x theta. So here, x is determined or defined by this equation. And x tilde, we don't have equation for x tilde, yet I want to restrict the process x and x tilde by this distribution constraints. So here, x and x tilde have the same distribution in the space of continuous functions. Over the time between 0 towards t or infinity, x theta and x tilde have the same distribution, and x depends on x tilde and its distribution with drift and diffusion coefficients. But here without reflections. So let me start with this model. Vi coefficients are smooth, assumed to be smooth. Initial values x0 theta, x0 tilde. Let me call it theta tilde as the initial value. Assume that theta, theta tilde, and x tilde are independent of the Brownian motion, which driving this equation. And this independence gives us direction, directed chain. So let me try to explain it a bit more. If we write v0t as dt or time variable, then we just rewrite in this way. In general, we can increase the number of Brownian motions or noise. But still, we want to add this restriction. X and x tilde have the same distribution, distribution constraints. For example, if we write vi t time x state mu distribution y, so let me remind ourselves. So this bracket is distribution probability rho of xt tilde are the same. So in particular, here is a distribution at time s of x. So distribution mu and y, which is a neighborhood process, x tilde. And so the dependence through y of this x tilde is coming to here. And assume that with some fixed constant u, we decompose into two components. U of b0, another smooth function, and 1 minus u. So u is a constant. We have weights. So u is a weights between u and 1 minus u assigned with neighborhood guy y, which is going to x tilde. And the distribution, let me call mu, is the distribution of itself. Because x and x tilde have the same distribution, here I write the distribution of x, but it's the same as the distribution of x tilde. If u equals 0, particular case, I chose u as a constant weight. If u is 0, there is no contribution from neighborhood guy. So we get a nonlinear equation called Makin-Brazov type, Makin-Brazov equation. On the other hand, if u equals 1, there is no contribution from the distribution. If u equals 1, then this is 0. Second term becomes 0, so that there is no contribution from the distribution. And let me call such this equation directed chain. And why we call directed chain, we will see a little bit more. So we started studying this type of equation about 5 years ago. The first result is this without reflection. Assume that Vi, the drift coefficient and diffusion coefficients are Lipschitz, smooth, nicely, and Lipschitz continuous, which means that the difference between Tx mu y and Tx prime mu prime y prime is controlled by Lipschitz constant Ct, as well as linear growth condition, so that we do not explode too much. And here, because we look at the difference between two distributions, we apply mu and mu tilde difference as a versus time distance 2 versus time distance W2. The first result I want to mention is there exists a solution, weak solution, unique in the sense of distribution. So here, uniqueness is that we want to look at, we want to look at the joint distribution, x and x tilde, driven by single Brownian motion, B. So we do not write driving Brownian motion for x tilde, but we assume that the distribution of x tilde is same as distribution of x. And so this is a unique existence and the uniqueness in the distribution, probability distribution. After this, so the proof depends on because of the Lipschitz continuity, this Picard iteration works very well, so that we can measure the distance between two distributions of x and the previous iteration, substitute into this equation, and we repeat this iteration, and it converges to the target distribution. And we also study about the smoothness of such solution to this equation, which is joint work with me. And here we want to discuss about with reflection, but let me try to motivate us. Starting point is to understand an interacting particle system of sparse network. So here sparse means this type of interaction. So network or graph with vertex 1, 2, 3 up to n vertex. We want to see the dependence between 1 and 2, 2 and 3, and 3 and 4, but we cannot see the direct dependence between 1 and 3. The dependence between 1 and 3 is going through dependence on 2, vertex 2. This is quite contrast to this picture on the left, looking at vertex 1 connects to 2, 3, 4 up to n. Vertex 2 is connected to 1, 3, 4, and so on. So this left picture is more dense, connected to each other. And sparse graph here is, it looks like chain from 1 to 2, 2 to 3, 3 to 4, and so on. The left picture has been studied in the context of mean field interaction, mean field games, recently studied quite nicely, and mean field games on graph, as well as like smoothness of the solution of a Makin-Brazov equation. Here is another example I'm interested in. Looking at the realized variance, this is the data from Oxford Mine Institute realized library, realized volatility variance library 3.0. This is quite old, 2012 to 2021. We compute, or they computed nicely and provided us the realized variance from the data. And from that, I computed the correlation between them and make a minimum spanning tree. So if they are close to each other in terms of the correlation, it is connected. So minimum spanning tree is if we want to see the minimum cost. So cost, if they are far away, higher cost. If they are close, more closely related, the minimum, smaller cost. So minimum spanning tree is to minimize the cost. So this represents relationship among realized variance of indices. Here it's coded with so DJI, Dow Jones Index, here, DJI, and we have SPX or, sorry, SPX and RUT, Russell 2000 indices. And the time series data looks like this from 2012 to 2021. And they are similar, they are not exactly the same, but we can see some spikes. So the variance, our volatility is going to become large compared to the other, like it's a clustering of the noise. So here from 2012 to 2021, for about 9 years, 10 years. And in the middle, we have a high spike and almost at the same time. And we also have around here another spike. This is due to COVID-19 pandemic. And we want to see those dependence, the time series for each index are somehow related. In this case, of course, this is not directed, it's undirected because of the minimum spanning tree. And we want to see how can we model to understand those dependence in the graph or network. So this is another application of this kind of idea. Motivation is generating some simulation or distribution. In this case, example is stochastic opinion dynamics. This is sorry. Back. So this is a picture of stochastic opinion dynamics. The original paper or the survey paper of Mosh and Admore 2014 from Simon Review, looking at formation of consensus. So we have some different opinions starting from a uniform opinion. And so this is a mathematical modeling of formation of consensus opinions. And so the sample, if we magnify, we have two rows, first row and the second row of the graphs. And the blue one is the same on the first row and the second row, blue. It's difficult to see, but blue one is original, like sample from the paper by Mosh and Tadmore. The model looks like this. YT depends on the distribution of mu t, y, and psi, this kernel component is this form, y, which is basically looking at the expectation, the difference between the position and expectation. And theta 1 represents the strength of dependence on the distribution. We measure the distance, sorry. We measure the distance from the expectation. That theta 1 here, theta 1 represents the strength, and theta 2 represents the length of dependence. So if theta 2 here is 0.2, and the range of the data is, let's see, between 0, 2 or 0 to -2. And based on the neural SD developed by Kidgar and Foster, Lee, and Lyons, the top row figures, time 0.1, time 0.3, time 0.5, time 0.7, and we want to simulate this dynamics. And the interesting part of this model is we have two modes in the model. So here, blue one is a real one, or the original simulation. And we want to learn about the data and simulate generating stochastic opinion dynamics from different methods. The first row is doing stochastic neural networks, SD-GAN, generated adversarial network. And second row, which represents our idea of directed chain. And we want to capture, we want to capture the two modes, like bimodal behavior of the distribution, and we want to understand how we can approach this two modes. So DC GAN, directed chain GANs for the bottom, and neural SDE for the top. And of course, it's not perfect, but we want to understand how we can simulate of this type with this idea of directed chain. Stochastic games, and I mentioned briefly, stochastic differential games on the network. So idea is here, let me briefly explain. Each player sitting on the node of the network, vertex of the graph, and player I minimize the expected cost as a game. And where the cost function depends on the state of the player's diffusion in an infinite directed network over the fixed time interval 0t. Network here, it can be randomized. So time 0, the network is formed at time 0. And depending on the network, cost will be determined. The question is how to understand equilibrium of the type of Nash equilibrium when the cost of player I depends on the network, and in this case, randomized. So player I does not know exactly the dependence in the network, but the player know how to determine those network randomized at time 0. And this idea of games, mean-field games, stochastic differential games, for the linear quadratic cost problem, it is solved quite nicely, as you can imagine. Carmona Fuchs-san, Daniel Lacker, Soret, and the deterministic random directed network, we try to understand in this way, like directed chain way. And the games on L-Dish-Renyi graph or graph on mean-field games, so those are related to each other. And here we are looking at sparse directed network. Sparse in the sense that network is connected not too many edges. We can also consider tree structure. So in this picture, directed tree. So here we have several layers. First layer, x of t, depends on x tilde 1, x tilde 2, x tilde 3, x tilde 4. And x tilde 2 and other guys for the second layer depends on the other guys, let's say x double tilde. And in that way, we can generate the tree and the dependence structure. And again, because of the distributional restriction, the distribution of x and distribution of x tilde have the same distribution. That kind of restriction leads us to try to model that kind of network or tree structure such that joint distribution of x, x tilde 1 to x tilde d, x here, and x tilde 1 to x tilde d, the layer 1 and layer 2 combined together has the same distribution as x tilde 2 and connected vertices double tilde, x double tilde 2, 1, x double tilde 2, 2, and so on. So in this case, we have 4 directed incoming edges for each point. And let me call d equals 4. Each vertex has 1 outgoing arrow and gets d incoming arrows from the other d vertices in the neighborhood. So this way we can make it a little bit generalized to the tree structure. when d equals 1, this is a chain. So now we come to the directed chain. So each vertex I depends on I plus 1 and affects the I minus 1. In terms of Ornstein-Uhlenbeck type dynamics, let me put xti depends on xti plus 1, dt plus dw ti. Starting from 1, I equals 1, index 1 to index n minus 1. And the last n, so let me consider here it looks like going forever, but starting from 1 to n. So n particles or n vertices with diffusions. And it looks like cycle or circle because for xtn, n's vertices, n's vertex depends on the xt1. So from 1, 2, 3, 4, and n also affects the, or n depends on 1. And the w are Brownian motions for the simplest case, and it looks like this. And this type of system has been studied before, I think, in different locations. And people sometimes call the Gaussian cascade of this type. Cascade because it's related to each other. As I mentioned, mean field is a different picture, which is each vertex I depends on the mean. I depends on mean, I minus 1 depends on mean or the distribution. So this is another understanding of the interaction. So if we replace previous slide, this xti plus 1 by mean, which is sample average, then this is generating to the mean field, to the mean field interaction. Then I'm interested in the dependent structure. So let me interpolate two interactions. So if we put u, as I mentioned, u is some fixed constant, represents a weight on the neighborhood and the mean. So previous picture, sorry. In the previous picture, we have expressed directed chain, directed network. We have mean field interaction, and we want to combine together in this way. So with weight to u, xti depends on xti plus 1, network in the neighborhood xti plus 1, and also depends on the distribution or sample average, empirical average, and it looks like Ornstein-Uhlenbeck. So in terms of the picture, so each vertex I depends on the neighborhood I plus 1 with direction, as well as sample average in this picture. So question, my essential question is, what is the difference between these two? As I mentioned, directed chain, cascade, Gaussian cascade, or mean field interaction. Can we detect or from the data, or can we detect from the observation? Or is there any significant difference between those directed chain or directed tree and the mean field interaction? And motivation, let me summarize as an introduction, which is effects of tree structure or in the volatility or network structure. And I also mentioned about directed chain, generative adversary network, systems generating the stochastic opinion dynamics as an example, and systemic risk problems of financial network. And now I want to discuss about regulation or reflection. So here we start with normal reflection. Can be more generalized, but let me work on the normal reflection in this way. So we restrict to one dimension, each node x and x tilde. So x is our interest, and x tilde is a neighborhood process, stochastic process. And previously, we put B naught and B1 more generalized, but let me simplify the notation to lift B, and the diffusion coefficient is 1. And this B is a drift coefficient, as I mentioned, with some weight U, B1 xxy, and we can take another function B2, but let me put B1 with weight U, and 1 minus U weight proportion 1 minus U integral of BI, B1, Sxz mu dc. So the second term represents mean field effect, mean field induction. First drift component is for the neighborhood part. And we assume, again, distribution constraints. Rho of x tilde and rho of x has the same distribution. And we have restriction LT is pushing to make it not to go into the negative side, but into the positive side. So that x of t is always positive or non-negative. And directed chain comes from this independence or filtration structure. So initial value theta, theta tilde, and x tilde is independent of the driving noise. So idea is that given theta, theta tilde, and x tilde, and we want to find the Brownian motion so that this x and x tilde and L altogether come into the same probability space, in the same probability space. So this is a same distribution. X tilde and x theta has the same distribution. And the first proposition is assume B1 is bounded. So here B1 is bounded and Lipschitz is continuous. And then the above equation has, again, the uniqueness distribution, weak solution. Weak solution because this x tilde is driven again by another Brownian motion, but we didn't specify Brownian motion. And again, proof is based on the Picard iteration. And now an idea comes from Schnitzman. And that's why I put bounded coefficient. But in general, as Schnitzman mentioned in that paper, those coefficients can be generalized. So B, and also we can put sigma, still normal reflection, and in higher dimension for the Schnitzman's paper. But for the simplicity of the notation, let me put in this way. So let me try to explain with an example. So for the particular case, we have this reflection term. And if we choose B1 as minus x minus 1, y, so the linear, but because of that neighborhood process and mean field induction, because of the linear, we integrate, we get expectation. It looks like Ornstein-Uhlenbeck process with reflection. But because of the expectation, we have a little bit more complicated. For a moment, again, without reflection, let's start with initial point is 0 for simplicity. The expectation is 0, so it becomes simpler. And I want to explain, we can solve without reflection quite nicely. So we have explicitly solve our Gaussian pair, x and x tilde, if we do not have reflection, local reflection term L. And starting from 0, we make it simpler. Idea is the following: because of the interaction is going to the next neighbor stochastic process. So in particular, if u equals 1, so what is u? U equals 1, which means that u equals 1, we delete this dependence on the expectation. Dependence on the expectation. If u equals 1, dependence is only on the neighborhood. So suppose that we know x2. The solution to the Ornstein-Uhlenbeck process without reflection can be computed quite explicitly. If we know the neighborhood process, solve OU process, Onsen-Uhlenbeck process, SDE, x1 is given by that. But we know that x2 and x1 have the same distribution. So x2 itself is given by another process, neighborhood process, x3. If we know x3, we can write down the solution x2 quite nicely. Let's substitute this formula x2 into this x2. In that case, as you can see, integral of exponential dB1 and the integral of the blue part coming into here, we have a double integral and x3. And we want to repeat. So idea is that because x1 and x2 are neighborhood, x2 and x3 are neighborhood, for the Ornstein-Uhlenbeck without reflection, we can write it down the solution, substitute one by one. Then we can write down x1 in terms of x3. And if we do another iteration, x1 is represented by Brownian motions b1, b2, and b3 and x4. And so we keep going. Then we can do some stochastic calculus. If we do this type of s minus u to the k minus 1 ds first using the Fubini type argument, then we have t minus u to the k divided by k. And because we have this type of dB ds or dB ds1 to dsk because of dB2u exponential ds, and if we substitute x3, we have first one, second one, and third one, and so on. So if we repeat this procedure, we get this type of integral. And then for this type of integral, we get this Poisson probability type kernel. So if we repeat many times, we get a sum of integral exponential minus t minus b to the k divided by k factorial. And we need a lot of Brownian motion to represent the solution. If we add more and more Brownian motion, Brownian noise, we can represent the solution. So the solution of the original equation without reflection can be written this way. So we can compute the covariance. This is a Brownian motion B. So taking expectation, this is a nice, still nice kernel. So we can take some summation. Mean expectation of x is 0. So integral of the sum of this Poisson process probability, or Poisson probability, but in the time backward, backward in the opposite time direction of the Brownian motion, we can write it down, mean is 0, and the variance covariance can be computed in this way. So nicely, the covariance can be written in terms of modified Bessel function of the first kind with parameter 0, or in general, we can write in this way. In particular, variance looks like this. So the modified Bessel function of index 0 or 1, and it grows like square root 2 and square root t for large t. And the covariance grows, so covariance between time s and time s plus t decays this exponential way. And one by one, we can compute this covariance between x1 and x2 with the neighborhood guy, or in the network. We can compute from the previous guy by iteration. Recursively, we can compute covariance in the space variables as well as the time variables. And from the covariance function, we can compute or simulate a sample path. So x, in this case, u equals 1. So x1 dagger, x2 dagger looks like this. So they are somehow, it looks like related. And again, the distribution of x1 and distribution of x2 are the same. So this is a case that u u equals 1. So we go back. So we use another u, but here u equals 1. What was u is a dependence to the neighborhood. If u equals 1, there is no dependence from expectation, and we can write it down this way. And in general, we can write it down with u between 0 and 1 for fixed u. U is coming here, and this one is hidden, but the same as you can imagine that this part is a Poisson probability. So here, this P0k is a Poisson probability or taboo transition probability because u is not necessarily 1. And we can generate the Markov chain, M, Markov chain, M in the state space N0, and generate a matrix Q. Qi I plus 1 is u going to forward from state I to state I plus 1 with u. And Qij, we cannot go back. From I to j, we get to 0. So generate a matrix of Markov chain Q, continuous time Markov chain, compute this transition probability. This comes into here. Yes.
Can you show 2 slides earlier, please? Once more, yeah. I had a question about this red quantity. So if you look at the exponential, you will have something going from a negative to positive or in the other way. So it means that for some critical S, you will change.
You mean fluctuation?
I mean, is it intuitive?
I forgot, but but I remember it's quite smooth. It's not going plus minus and so on. It's more smooth, decay exponentially fast. Thank you for asking. And it has a dichotomy. So as I mentioned, I'm interested in how to understand the relationship between the processes and neighborhood. And the variance of xtu, if there is no interaction from the mean field, the variance grows, the order of square root t. So although we set up in the Ornstein-Uhlenbeck is attracted towards the neighborhood, in the long run, variance of xt is going to grow. And if we have interaction from the mean field, in that case, it's still stationary. So if we take integral from 0 to the infinity to this Bessel function, this is finite. And more generally, with this idea, goes to stochastic evolution equation, Dawson and Cariampo, and Astaire, Bass, and Perkins, for more general case. But let me continue a little bit. So idea is this idea, if we put Q formally as a Markov chain Q matrix, and xt is those xk from 0, 1, 2, and so on, infinite many. Formally, we can write it down, the solution of OU process with this type. So exponential t minus s to the q to this semi-group structure comes into the inside of the stochastic integral. Its stochastic integrand is exponential t minus s to the q. So with this idea, maybe we can choose another matrix. So let me summarize. X1, if e equals 1, we have a Poisson process. And this pk is a Poisson process probability. So if we run Poisson process and associated with Brownian motion, then we can write it down, the process X1. If we choose a compound Poisson process, N tilde, and then we can write it down in this way, pk tilde, and the matrix is q tilde. Q matrix looks like this. So again, which is one-sided, and so this is directed chain. We can also consider both sides. So here in the past, so far we only discuss about one-sided direction, but we can also consider double-sided. So if we choose q tilde, 1/2, then we can do both-sided. So previously we considered one-sided interaction, but we can also consider double-sided, both-sided interaction through this mechanism. And another modification is that so far all your process but attracted towards a neighborhood. But if we repulsive from the neighborhood, so x1 minus x2, so going to the repulsive relationship, then variance is growing very fast, exponentially growing. So I'm sitting here and neighborhood, our friend, and try to separate the repulsive way, then variance grows very fast of the process. And with reflection, so coming to the with reflection, then we have now so previously we have this part, this part, and Brownian motion. But because of the reflection here, it is more complicated. And x tilde u, we have a Brownian motion and the reflection component, local time component for the corresponding process for each node. So accumulation of the local time in space is coming into this plane. So it generates some positive drift. In particular, if u equals 1, limit of variance of xt1 goes to infinity quite fast because of the accumulation of the local time from the neighborhood. Although we discount it, but still going to the infinity. And we want to mention about this. So because we somehow we can simulate, but more systematically we can simulate in this way. Consider a finite system, xt1 to xtn, n particles, and we generate for this particular model with reflection, bt xti, where m, here m is taken as an empirical measure, substitute into here, which is the usual n-dimensional n-particle system, Brownian motion, and local time for each I. So LTI is a regulation term, reflecting part for each particle I, so that each particle is non-negative. The boundary, because we have only n particle is going to relate it to the first particle. So 1, 2, 3, and nth particle is going to going back to first particle. And take n goes to infinity. The circle becomes bigger and bigger. And because of the chain or one linear structure, as n becomes larger and larger, the particle xt1 and particle xtn, the dependence between two particles, node 1 and node n, dependence becomes smaller and smaller. So basically, we can cut this dependence between n and 1 in the limit. So for this particular proposition, let me continue with B as weight U, 1 minus U, and neighborhood interaction and mean field interaction. And for this case, because the reason why I want to put xn connected to x1, if we write xn plus 1 as x1, then they have the same distribution because of the definition we looked at. So here xti depends on xti plus 1, xtn depends on xt1. So if we write xt1 as xtn plus 1, then we have circle back so that they have the same distribution because of the in terms of the space in the graph, they have the same distribution because same drift and independent Brownian motions. Distribution of xi is same as distribution of x1. And distribution of xi and I plus 1 is same as x1 and x2. But we cannot expect x1 to x2 as same as xi and xi minus 1. We have an order. And we define a empirical measure for the marginal distribution and empirical measure for the joint distribution. So xti plus 1, xti plus 1 as a joint empirical measure. The difference from propagational chaos result in the beginning, although we assume independence so that the initial distribution converges as n goes to infinity, the distribution of time t as n goes to infinity still dependent. We keep this dependent structure so that the propagational chaos in the sense that in the limit as n goes to infinity, the dependence becomes independent in the propagational chaos. Here we keep the dependent structure as n goes to infinity. So as n goes to infinity, initial distribution m0n marginals goes to the distribution, and joint distribution mtn converges to the point mass deterministic measure by process mt, which can be characterized as integral equation. And here we have deflection components, so g prime 0 plus equals 0 for this family of test function Sm. So this infinitesimal generator is dependence from the neighborhood, dependence from the mean field component, and we have we need the joint distribution. The joint distribution, and we cannot separate joint distribution in terms of the product of marginal distributions. And proof uses a marginal problem approach, Schinaga and Schnitzman. And Schnitzman tried to do a propagation chaos in a slightly different formulation, but the idea is using the marginal problem or sub-marginal problem in this context because of the reflection. And summary, let me summarize. We try to introduce or share about the idea of directed chain stochastic equation with reflection and of this type. And we try to look at particular approximation of the joint distribution of x and x tilde. In the limit, or in particular, x and x tilde are not independent. So we want to understand the network in the limit, contrast to the propagation chaos. Contrast to the propagation chaos, the limit is x and x tilde are still dependent. We want to understand the dependence between the neighborhood. And one simpler way, maybe simplest way to capture dependence is one introduced by this type of SDE. Try to look at dependence through method of stochastic analysis. So fluctuation and smoothness is, I didn't have a chance to discuss. And there are some applications, mean field games, stochastic games on the network, filtering problem, mimicking problem, and we consider also generative adversarial network. And let me stop, and thank you very much for your attention.
Thank you very much. Do you have any questions or comments?
Thank you for interesting talk. I have two questions. The one is, are there some conditions about existence of stationary distribution?
That's a good question. For without reflection, we started with without reflection. We know somehow a little bit, but stationary distribution of nonlinear type, because of the dependence of the distribution in the coefficient, we do not know much. And even recently, we have several papers. So for the particular case, Ornstein-Uhlenbeck case, without reflection, if we have interaction through distribution with mean or expectation, then we have a stationary distribution. Stationary distribution is still Gaussian. And for the general case, I do not know how to handle.
And my second question is the following. You have the first equation, and now let's write the second for x tilde of the following way, but plug another Brownian motion independent b with tilde and x theta instead of x tilde. And you have pair of equations, a pair closed in a closed form. So, and it looks like multidimensional midfield. Is it correct or not?
Right. So we try to formulate in this way. There is a distribution constraints so that implicitly we expect those x tilde has the same type of equation.
Yeah, but
you
plug for equation x tilde x from the first one.
So that's the double direction.
So you can add third, fourth, and obtain cascade like you did. But is it the same if you just write the first one?
So we have a similar discussion among co-authors, and our understanding is the following. So if we have a special structure, linear form like Ornstein-Uhlenbeck, we can do both directions. So x depends on x tilde depends on x, and the same distribution, and we continue in this like infinite chain. So for example, we looked at this is a special case Q tilde, Q matrix, going to random walk on the next symmetric random walk, 1/2 and 1/2. Then this is, or we can generalize to several ways and in both directions. And because we want to put the process X is adapted to that filtration, and we add additional Brownian motion in that way. So here we have an explicit solution, and for the STE, we took this approach. In general, like for the network structure, directed not only one-sided, both directions. And if we have only finitely many, then we do usual way, finite many particle system. If we take infinity, then what we do is only the linear case so far. But I like your question, and we try to understand, can we do both ways in an interesting way?
Okay, thanks.
Thank you.
Does it make sense to add one more parameter in front of the local time and to have a kind of stickiness?
That's a good question. So boundary behavior here, we have a normal reflection, but I am thinking of reflection local time from the x tilde as well. For example, interaction from the local time from x tilde, that's also possible in some sense.
Mm-hmm. Any further question? So if not, let's thanks to Tomoyuki again.
Thank you.